Right? Okay. Welcome everyone to another Infosys Connect Panel seminar. It's a pleasure to have Dr. Vivishek Sudhir come here today and give this seminar. Vivishek did his PhD in the Swiss Federal Institute of Technology in Lausanne in the group of Professor Tobias Kippenberg. And what he's going to be telling us about is the bulk of the work he did during his PhD at in Professor Kippenberg's group. He graduated in 2016 and continued there for another year as a postdoc before moving to the MIT LIGO laboratory in August of 2017, where he is now trying to apply the lessons learned from tabletop experiments to large-scale gravity wave interferometry detection. So I think Vivishek will take us through this journey and look forward.
Hi, thanks. So thanks for having me here, and I'm really privileged to be here. And thanks for turning up for the seminar. So I'm ostensibly going to talk about how we have done certain precision measurement on a tabletop scale experiment in Switzerland, and how that sort of informs us and what sort of lessons we've learned from doing that, and how that can be applied to improve the sensitivity of really large scale interferometers such as the ones used in the LIGO detector. So I'm basically going to talk about how we perform these quantum measurements and how that helps us do metrology using a macroscopic mechanical oscillator. So the standard problem when such a title is mentioned with quantum and macroscopic in the same sentence is one of discordance. And historically, this sort of discordance has been raised multiple times, famously for the first time by people like Schrödinger, who said, well, if you apply things like quantum notions like uncertainty to macroscopically tangible and visible things, then the implication of this blurring that is caused by, that is sort of implied by quantum mechanics seems just simply wrong and unacceptable. But of course, such a discordance doesn't exist if you think of quantum mechanics applied to microscopic objects, like microscopic mechanical oscillators in particular. So here, for example, in early pioneering experiments in Hans Demar's group in Washington, they tried to study single electrons and single ions trapped in a pinning trap. So you have a harmonic oscillator, and you could see on an atomic ion, for example, quantum jumps. That's kind of the first time that quantum jumps were ever seen in any system. And there's no discordance here because it's a microscopic system, and people are happy to accept that they are naturally quantum mechanical. And since then, over the past 15-20 years, ion trappers have sort of pioneered efforts to render tiny mechanical oscillators into grossly quantum mechanical states. For example, here you see a single ion, its motion basically prepared in a single phonon Fock state. So it's got a negative Wigner function, so that's very non-classical. And because of this, discordance between what has been experimentally done microscopically and our expectation for the macroscopic world, which is this, not certainly quantum mechanical, there's been this, sort of cartoonish picture of what one should expect with regard to what is microscopic on this side, what is microscopic on this side, and what is macroscopic on the other side. So the microscopic stuff, photons, electrons, atoms, are sort of innately quantum in some sense, and then the classical domain, like suns, planets, people, and quantum fluids, sort of are on that side of the boundary, and then they sort of merge in the middle. And gravitational wave detectors sort of happen to straddle this boundary in a certain sense, which I'll make clear. So the question really becomes, in the context of such a cartoon, can you sort of extrapolate this boundary, apparent boundary at least, all the way to the extreme end and sort of put systems which are grossly macroscopic into and basically exhibit quantum properties of these grossly macroscopic systems. And gravitational wave detector happens to be the thing that's supposed to straddle this boundary. Why do I say that? So this is the LIGO Hanford Observatory. It's a long Michelson interferometer with a 4 kilometer long arm, and the detector basically, the basic optics of that detector is as follows. So there's a laser, it gets coupled into the symmetric arms of a Michelson interferometer, and the arms actually have a Fabry-Perot cavity inside to resonate the light. That arm, each arm is about 4 kilometers long, and then light comes out and hits a photodiode, and that's how the detection is made. So any differential motion offset of the 2 Michelson arms basically gives you some power here which you detect. And indeed, the end mirrors here are sort of not just macroscopic in a nano sense, but macroscopic in a human scale sense, right? So that's one of the end mirrors. It's about 40 kilograms heavy. It hangs on glass wires. It's about a big. So that's very human. So how is this thing straddling this quantum classical boundary really? The answer actually comes from a theoretical prediction made over 20 years ago, which is this famous paper of Carlton Caves, where he says something very simple, which I'd illustrate like this. So think of one of these arm Fabry-Perot cavities, which is sort of cartooned here. So you have one end mirror which is sort of mobile, and then another mirror, so the one closer to the beam splitter here, so this mirror and then that mirror sort of mobile, and this can move. And then what happens is how do you try to make a measurement of this end mirror? So what you do is you shine light in. When the end mirror moves, it sort of gives you a phase shift on the light leaking out of the cavity. If you look at it on a phase space picture, so that's sort of the complex phasor picture for the electric field coming out, you would see the motion of the end mirror as sort of a classical modulation of the phase coming out. So your ability to infer the position is simply impeded by how well you can make an inference of the phase coming out. And that ability is sort of impeded by fundamental quantum fluctuations in the electromagnetic field. So the electromagnetic field is a quantized entity, and the phase fluctuation, there are fundamental phase fluctuations on it, whose magnitude sort of go inversely proportional to the square root of the number of photons you use to make the measurement. So well, the idea is simple, right? Okay, if you want to make a more precise measurement, you want to get rid of this problem as much as possible, which simply means that okay, let's simply amp up the number of photons you use to make a measurement. This sort of puts the blob further away from the origin. It subtends a smaller angle at the origin. Problem solved. Well, not quite. That's what Caves' problem was, which is that light is not just an electromagnetic wave, it's also a stream of particles. That's just the wave particle duality. So if you increase the number of photons used to make a measurement, these photons, when they recoil off the mirror, it imparts a certain recoil momentum, a force, a back action force, and that force is just the radiation pressure force. So that is just basically proportional to the number of photons in the cavity. So that's a quantum mechanical operator. That by itself is not particularly quantum. That's just the third law of Newtonian mechanics, in a sense that is action and reaction. But the quantum mechanical point here is that this force actually has irreducible quantum fluctuations in it, which is to say that when light is in sort of a coherent state, there are fluctuations in the force which are directly proportional to the number of photons. So now here is the tension. The tension is the following. On the one hand, you want to make more precise measurements by using a large number of photons. On the other, you disturb the motion of the mirror when you make a more and more precise measurement. So that's just Heisenberg's thought experiment. So this is how the LIGO interferometer is a quantum mechanical thing. It can be susceptible to this sort of a mechanism. Never been observed, predicted for 30 years. And in fact, this is sort of the state of the art in terms of the noise budget of LIGO, where we sort of see how far we are away from meeting this sort of quantum mechanical limit. So this is sort of the LIGO output calibrated in displacement units. So that's a spectral density, and that's kind of the typical observation frequency of LIGO. And the red is sort of the sensitivity curve for LIGO when the first detections were made in late 2015. So what you see in the blue curve is sort of the quantum mechanical contribution to this total noise budget. So on the high frequency, you see this phase short noise, and in the low frequency side, you sort of see the quantum back action that limits you. And sort of when there's an optimum here in frequency, which is sort of called the standard quantum limit, which is sort of the lowest point allowed as a compromise between these two contributions. But the point is that although this prediction and such noise curves have been around for the entire history of LIGO, nobody has actually seen this because most of the LIGO noise at these quantum back action frequencies are dominated by technical noise, which is sort of getting solved at this point.
Vivishek, quick question. I have typically seen these curves, the crossover curves, as a function of photon number, right?
Right.
So here you are plotting them as a function of frequency.
Right.
So how do I think about this?
Right. So in terms of photon number, what you should think of is so what is the mode here? So what is the mechanical mode here? So the mechanical mode is just the fundamental pendulum mode of this suspension. So it's just a mirror hanging on a pendulum, and that has a resonance frequency here, so about 10 hertz. That's the green thing here. So the green thing is just the thermal motion of that pendulum, And then you do have a quantum back action contribution over here. So suppose the blue is in fact supposed to be just the peak, but then LIGO folks just plot the broadband part of it because they don't really care about the resonant part anyway. So this blue would actually go up, come down, and then go down here. And the plots versus frequency, that plots versus photon number that you see is sort of the quantum back action contribution under the peak measured as a function of photon number. But if you stay at a fixed photon number and look at how the two contributions go in frequency, then it's sort of this. So it's sort of complementary. I mean, in nano tabletop, nano optomechanics, we don't actually make broadband measurements. Actually, we do, but only since last year. And sort of, that's sort of the discordance here.
So will it be the SQL in this?
That's exactly right. So this minimum point in the blue curve is exactly what the SQL would be. So now this is what the prediction is, but nobody has actually seen quantum back action in any system, let alone LIGO, where things are just technically hard. But then once LIGO sees QBA, you need to have techniques to suppress and evade quantum back action so that astronomy is not limited by just this silly sort of noise. So one of the things that we did at EPFL was to really try to study quantum back action in a tabletop controlled experiment and to develop a microcavity interferometer that would be susceptible to this quantum back action force. So since the quantum back action force is extremely small, what you want is an exceptional force transducer that can take the force, the small force, and create a large enough displacement that you can then measure. So for the mechanical transducer, we chose to use a low mass, high Q mechanical oscillator, which is sort of ubiquitous in all sorts of small force measurement scenarios, like for example in Dan Ruga's group at IBM, where they did single spin detection with a AFM cantilever. And to transduce this motion, we used an optical microcavity whose benefits are that it's an extremely low mode volume optical cavity with an extremely high finesse. So we're talking of optical Q factors of 10 to the 6, 10 to the 7, 10 to the 8 even in the best cases. And these are sort of were used to do various cavity QED sort of things where low mode volume is sort of a big thing. So we sort of tried to integrate these two things in a novel fashion, and the idea is that you basically take the best of both worlds and then sort of try to maintain their good properties while still integrating them. So it's sort of a fabrication challenge which took about several years for us to get a handle on. But ultimately what we were able to do was to actually retain the good mechanical properties. So mechanical line widths of a few hertz with fundamental frequencies of several megahertz. So that's a Q, mechanical Q of 10 to the 6, optical Q of 10 to the 6, 10 to the 7, and then sort of tightly integrate them by placing the beam on the steeply falling evanescent field of this microcavity. And then by making that gap extremely close, you could actually get vacuum optomechanical coupling rates of about 20 kilohertz. So what that number means is the following. So imagine that the beam actually executes just its ground state motion, right? If it's in its ground state, it's got some RMS motion, and that motion would change the cavity frequency by about 20 kilohertz. So that's what this 20 kilohertz number means. So that's a large number. So on a 10 megahertz cavity, you want to measure a 20 kilohertz shift. That's not hard. It's about 50 nanometers. And below about 20 nanometers, we sort of see van der Waals sticking. So that's we are sort of operating at the limit of what's possible here. So this sort of device is sort of a prototype for this field that has sprouted in the last decade or so called cavity optomechanics. So our device is sort of here, 10 picogram mass mechanical oscillator oscillating at megahertz frequencies. LIGO is sort of on the other end of the spectrum, and sort of the motion, in our case the motion of this beam gives you a phase shift of the light exiting the cavity. That is sort of exactly similar to this Fabry-Perot geometry here, hence the analogy between this and this. And in fact the analogy is more than just a metaphor, it's actually formally true. So you can write down a Hamiltonian where the interaction part is sort of applies across this entire regime in size and frequency. So the idea of making a microcavity interferometer susceptible to back action is to really have something where its so-called cooperativity, which is a sort of figure of merit for how good of a sensor this is, to basically realize something whose cooperativity is as close to unity as possible. And here what we mean by cooperativity almost always is a single photon cooperativity. So what that number tells you, it's sort of like a dimensionless figure of merit that tells you, so if cooperativity is less than 1, you could think of it as, well, how much, by what fraction does the wave function of the mechanical oscillator move compared to its 0 point extent when a single photon bounces from it. So that's basically what it means when the cooperativity is less than 1. So in the perturbative regime, when it's larger than 1, that sort of story doesn't well hold true. In any case, we've basically managed to realize a device with a single photon cooperativity of unity or slightly above unity, in fact. And that is sort of the state of the art in cavity optomechanics at this point. Sort of devices that feature significantly larger cooperativities are just clouds of atoms which are stored in optical traps. So they're not really solid objects. So the way we make a measurement of this device, of the mechanical oscillator.
The measurements done by the group in McGill, their cooperativity is much better, right?
No, not really. Not really, because Jack Sankey's paper or Simon Groblacher's paper from PRL, they don't actually feature, they say a predicted cooperativity, that is not a measured cooperativity. So they claim that their mechanical oscillator has a better Q, which is demonstrated in the paper, good. Both the coupling strength and the cavity line widths are just estimated from what they would in principle get if they use the best cavity in the world. But actually it is known from later experiments since then that if they take their trampoline resonators and put them in a cavity, the cavity line width deteriorates by a huge lot because of clipping losses and scattering loss from the cantilever, from the trampoline resonator. So it's not a demonstrated cooperativity, it's a cooperativity.
What is their cooperativity?
So their predicted cooperativity is about 5, single photon cooperativity is about 5. Their observed cooperativity, which I know from talking to Jack actually 2 weeks ago, is about 0.8, 0.9, because they do take a big hit in the cavity line width when they put the trampoline in.
You said 0.8.
0.8, yeah. So no, it's not that far. But except for the fact that we sort of reached this regime in 2015, whereas Jack's paper came out in 2016.